Hello everyone, this is Dr. Hopkins, your sometimes virtual and sometimes face-to-face instructor, narrating the next in our series of videos for Chem 472, where we define heat. So I'm going to start off with the slide from the last video about work. It was relating the first law of thermodynamics, and in total internal energy change is both heat and work. Work we talked about last time. In this case, we're going to describe heat. Okay, so heat is actually a much trickier concept to think about than work, and actually is a much trickier concept to get your head around. But typically we think about it in terms of how it, I say operationally, how it affects things that we interact with, right? So in other words, does the temperature change? The temperature change, that indicates heat flow. Okay, so then that means that heat's something that only appears at the boundary. Actually, both heat and work only appear at a boundary. We don't really care what's happening internally of our system and surroundings. It always flows from hot to cold. Okay, so it's down a temperature gradient. So we go from hot temperature to low temperature. Heat is flowing in that direction. There's no real theoretical reason why that is. That's just kind of observation. We always notice that. You put your hand on a hot burner, you burn your hand. The burner just doesn't get cold. Your hand gets hot. Molecularly, it's basically random motion of molecules or atoms. And if we're talking about gases, just like work, it's a path function, so it's not a state function. It's an inexact differential, and it can be converted to work, but not completely. So you can convert some of your heat to work, but not all of it. And that's due to the constraints of the second law, which we'll deal with in a few weeks. So we once again have our convention of how we define heat flow. So if the dq is greater than 0 or positive, we're adding heat to the system. If it's negative, the heat is evolved from the system. This is something you might have thought about from when we were talking about enthalpy in Gen Chem. But anyway, that's the same kind of sign convention. Right? So sign just tells us the direction of heat flow. Okay, so how do we determine heat? As we said, operationally. So we're going to define heat capacity, right? So in a way to measure it. And basically heat capacity is the ability of a system to store the energy without a given rise for a given rise in temperature. And so we have a simple expression, dq over dt. C is the variable we're going to use to describe to define heat capacity. The measurement's very simple. It's calorimetry. You may have done it with a coffee cup, a little styrofoam coffee cup, and you basically just add heat and measure the temperature. Okay, so the measurement is pretty simple. Molecularly, what happens if you add heat and the temperature doesn't go up as much? So let's say we add heat to two separate systems, and the temperature doesn't go up as high. Where is that heat energy going? And it's actually going into activating internal modes of motion, or internal modes or degrees of freedom. And so if we're talking about molecules or atoms, that means translational motion. So that's movement of the center of mass through space, x, y, z. Rotational motion is about a rotating around a moment of inertia. Vibrational is as bonds stretch and wag and so forth. And then electronic motion as electrons go from one state to another state. Okay, so all of these are all internal degrees of freedom. So if you add heat, for example, you're going to add more vibrational energy. If you add some heat, you'll add more rotational energy. And in general, specifically, all of these degrees of freedom are actually quantized, with the exception of translation. So we would require quantum mechanics and actually then fold that into statistical thermodynamics to model rigorously. But we're gonna come up with a classical treatment for heat capacity. And we're going to use the equipartition theorem. So basically what this means, we're going to only consider translational, rotational, and vibrational degrees of freedom. Electronic generally requires lots and lots of heat to activate an electronic energy. And at that point, classical mechanics fall apart, and we would need to evoke statistical mechanics anyway. So we're only going to consider those degrees of freedom. And then we're going to consider that if the degree of freedom is activated, it's activated to an average kinetic energy related to its temperature. Okay, so if you remember from your physics, the kinetic energy is this quadratic in terms of the motion, right? But then if you remember back when we talked about the ideal gas, one of the assumptions was then that the average velocity of the gas particles was related to the temperature. So we can also relate this quadratic in terms of temperature, where Kb is a Boltzmann constant. And I don't have the value of the Boltzmann constants, but it's about 10 to the minus 23 joules per Kelvin. And so if we have a gas, a monoatomic gas particle translation, and it can translate in 3 dimensions, so we would have 3 separate velocities or quadratics, and then we would add those kBTs up, and we have 3/2 kBT. Okay. Now, just to let you know, the Boltzmann constant is, if you multiply the Boltzmann constant times Avogadro's number, you get R. Okay, so that's where it comes out. It's a molecular, whereas R is the per mole. So we're typically going to talk about per mole. So that means that the kinetic energy, or the temperature, is a 3/2 RT. Okay. So if we have atoms, so where we have no rotational, no vibrational, we could have electronic, but we're ignoring that degree of freedom, so we only have translational degrees of freedom. So the internal energy of that atom is its internal energy at 0 Kelvin. So that's all of the kind of physics, the physical properties. So this absolute energy, if you put Einstein's equation in there, you could figure that value out. But it's the energy the system has based on the mass and etc. And then it's going to have kinetic energy at 3/2 RT, so depending on the temperature, right? And if we have a diatomic molecule, we can assign the same. So our internal energy is, at a particular temperature, is the 0 Kelvin internal energy, and 5/2. So a diatomic molecule has 1 vibration. So we have 1 bond that can stretch. And then we end up having 1 moment of inertia in a diatomic molecule. And I have a little table, it's actually not much of a table, that describes the degrees of freedom. So every molecule atom has 3 translational degrees of freedom, X, Y, and Z. And then rotational, there can be up to 3. So you can have a moment of inertia around the X, Y, and Z axis of the molecule itself. And then vibrationally, if it's a linear molecule, it's 3n. So n is the number of atoms in the molecule minus 5. And 3n minus 6 for nonlinear. So you can see the number of degrees of freedom. So what we would add to this can go up quite large for very large systems. So we go back to heat capacity. So now we have how internal energy changes with temperature based on the equipartition theorem. So we start with our initial definition. We're going to hold volume constant, which is we're going to do an isochoric process. So we'll put this C with a subscript V. That means it's under isochoric conditions. This would be the heat capacity. And so then we just make this a partial derivative holding volume constant, right? So then if we go into our first law expression, du is equal to Q plus work, if volume is constant and we assume only PV work. So if we have a gas and we're not worried about any kind of electromotive and other kind of definitions of work, remember the definition for work was minus PdV, but the dV goes to 0, right? So this term goes away and we're left with Q. So the U and Q, or the change in internal energy and change in heat, are the same. So that means our heat capacity is this partial derivative here with respect to U. Well, now the equipartition theorem we have an expression for U. So we substitute that in, and now we're just going to insert that result for a monatomic gas, right? So this is the partial derivative of U with respect to T, 3/2 RT. Well, the U at 0 Kelvin, it's not changing with temperature because it's defined at 1 temperature. So that derivative is 0, right? And then the derivative of 3/2 RT, or the derivative of T, the constant pulled out, is 3/2 R. And so we know that our heat capacity using the equipartition theorem at constant volume for a monatomic gas would be 3/2 R. And likewise, based on our definition before, the heat capacity is 5/2 R for a diatomic. And it would go up as we increase the number of internal degrees of freedom for constant volume processes. So next time we'll expand on this and then explain a little bit how this works in terms of the first law.